Hi everybody, I'm Chris Kanish and this is CS361, Systems Programming. Today we're going to be talking about signals, and we're going to be talking about things a little bit differently. Typically I record a couple of videos, 1, 2, 3, I cut them down and get rid of every and weird pause and false start. But today I'm going to experiment a little bit with doing this in one take, just getting through the things that I want to get through. Let me know in class or however you want whether this was just as good as the other types of videos or whether you would like to go back to the more chopped and cut up videos where there's lots of cuts everywhere showing what I did wrong or getting rid of everything that I did wrong and going through right all at once. Okay, now let's get started. Signals. This chapter was long, right? It was quite a bit. Signal handling is a relatively uncommon corner of systems programming, but it's still super important for our understanding of how process control works. So without it, we wouldn't really be able to interrupt runaway processes. We wouldn't be able to allow processes to safely exit. Our shells or other programs that control other programs would have a really tough time actually figuring out what the heck is happening. Signals are this fundamental thing that allow us to do inter-process communication between different processes, but in a very different way than you would when you're actually writing a program that just does work. As we're going to see later on in class, there are a lot of ways for one process to send messages to another process very explicitly, and the signal mechanism is like that, but it's a very specialized tool that's used in this interrupt-driven way rather than in an explicit, I'm going to wait to read something from process 1, I'm going to send something over to process 2 type of way. This is primarily for unintended, unexpected things like my child died or a file descriptor became ready to read. These are things that you're not typically going to want to deal with. And the biggest, probably trickiest part about this is that this is our first tiny little step into user level concurrent programming, where we're running one thread of control, for instance, our main thread in our program, and then something happens, and then our code starts running someplace else. And we explicitly have to make sure that those two pieces are working together the way that we want to do that. Okay, so one other, okay, next thing. This is where I get mixed up just a little bit. I'm going to go through everything we got here in these slides. Just go over some of these very important pieces of information about the concept of signals. And this is going to be mostly review of the stuff that was in the book, but overall it's going to be the basics, the straightforward, important stuff about signals. So without further ado, recall that we have exceptions. We have this concept of a user level process doing something. It's on a specific instruction. Something exceptional happens, and rather than executing the next instruction there, it goes and does something else. And then it's either going to return back and retry that, it's going to return back and do the next instruction, or it's not going to return at all. This is what happens when there is kernel level exceptional control flow, right? We switch over from being in the user space mode over to being in supervisor mode, where we can do lots of stuff like kill processes or create new ones or run system calls, all that stuff. And then we go back down into normal mode. We go back to Clark Kent instead of being Superman. With this, there's no way to tell the process, hey, something happened, outside of like stopping it and giving it this information. What we get out of the signal mechanism is something that allows us to send these messages back and forth, but it's not going to be as heavyweight or as disruptive as it is in the typical interrupt style approach, but it's still going to be it's going to be disruptive, just not as disruptive. So the signal, the most basic thing we have here is that signals allow the kernel to send a small message to a process, and signals correspond to different types of system events. There are user-defined signals, which we will use for examples a little bit later on today, but those are going to be less common. Those are a weird way to use the signal mechanism, where mostly what we're using signals for is exceptional things that a process needs to respond to that is outside of their normal operation. So some of the signals that we have here are things like SIGINT. So the most important things that we typically see are SIGINT, SIG-SEGV, SIG-KILL, SIG-QUIT, SIG-CHILD. These are all really, really important ones. SIGINT is when you hit Control-C on the keyboard. What's really important here, I've got a little aside I wanted to go over, is that when you typically type on the keyboard, you're not causing exceptions to happen. There's no exception, there's no interrupt. All you're doing is writing individual characters to a file. And yeah, writing characters to a file, if you were in a user level program, would actually cause a context switch. It'd have to be a syscall, etc. But the driver for the keyboard or the universal serial bus or the teletype, the virtual terminal that you're using, isn't going to have to do that. It's just going to be reading these bytes in from this device, and they're going to show up in that buffer. And as soon as somebody calls read, they're going to receive those bytes. That read call is a system call, right? That is going to be exceptional control flow where we jump over, but it's very different from a Control-C on the keyboard. When I hit Control-C on the keyboard, I'm actually triggering an interrupt to happen, and then the signal gets sent to the process. And we'll see a little bit later on what happens when I do that. And it's fundamentally different than when I'm just banging on the keyboard normally. We can send this kill signal to processes that will instruct that process, will instruct the operating system, in fact, to stop that process, dismantle it, take it off the CPU, mark it as stopped and never to be started again, things along those lines. We receive a signal when we do an illegal memory access that causes a segmentation fault. That is not something that just immediately zaps our process right away. Instead, it's something that gets reported to our process as a signal. And this is why when we're debugging with GDB, we can actually set a trap on that SIG-SEGV. What GDB can do is it can say, aha, I am debugging this child process of mine. I am going to instruct the Linux kernel, hey, when this tries to do this illegal thing, don't just kill it like it was a normal running process. You should instead transfer control to me so that I can take a look at what the heck is happening. And that's super, super helpful. And then SIG-CHILD, we'll see that. I think we saw that a little bit already when we're talking about additional processes. This is the signal that gets delivered to our process when one of our child processes has died, has exited. Now, we're going to get a little bit into this idea of sending signals. There are a few very, very important concepts that I want to talk about here, because when we first think about it, signals and interrupts sound like there's a thing that is immediately going to get sent to our process as soon as physically possible, right? Like we've been talking about interrupts and exceptional control flow and interrupting running instructions, right? But all of a sudden we're switching over to signals, which sounds similar and is being used in a similar way, but the way that it actually gets implemented by the operating system is very, very different. When a signal gets sent to an individual process, it will, like, sending the signal raises a flag. Like if you think of old-timey mailboxes where you've got that nice little red flag on the side, sending a signal raises a flag that says, hey, there is something in here that you have to take care of. It does not immediately cause the mail carrier to show up and take it out, right? The mail carrier doesn't teleport to your mailbox. The mail carrier only comes around and takes a look at it whenever it actually handles your running process. And if the mail carrier is in the process of like sorting the mail outside of your house, they're not going to immediately stop sorting that mail to look at your sweet red flag that you've just put up. So let's think about this mail carrier analogy, because I do think it maps onto signals pretty well. And there are very important differences between what we've seen already of exceptional control flow immediately taking over and signal handling, which only happens on switches from kernel mode to user mode. That's going to be the key cruxing. If there's one point that I think a lot of people get tripped up on with signals, is that signals only get handled when your user level process does a context switch or from another process to yours, or when you do a context switch from going into the kernel, say for a system call, and then back out of the kernel to end that system call. when the kernel gives control back to your user level code, that is when it decides to actually process that signal by calling your signal handling code. I'm getting a little bit ahead of myself, but I can't stress this part enough. This is where our analogy breaks down a little bit, right? I said there's just one little red flag and you can raise it and lower it, and that says whether or not a signal needs to be delivered. There's actually lots of them. I think there's 255. I'd have to double check, but you can have lots of different pending signals for a process that have their flags raised, and each of them does need to be handled by that running process before it moves on and does whatever else it wants to do. So this is something that always happens to me. I explain the thing that's on the next slide because I forget what it is I had on that slide. But yeah, here's in text what I had already mentioned on the previous slide. When the kernel, when the process switches back from kernel mode, it checks to see whether there is a pending signal, and it checks to see whether it needs to do something based on that pending signal. So we can take a look at this example here. We've got one process on one side, we've got another process on another side. So say the process on the left is the actual kill command that you have from the command line on bash. You can just type kill space and then the like dash p or something along those lines. But in this case, we're trying to send the sig kill signal to process 35. When we do that, in our kill process, we don't immediately go over there and say, hey, suspended process 35, I'm going to kill you right now. Process 35 is going to sit there waiting until it's going to run. Usually it'll run very quickly, but it's not going to actually be received until the process 35 gets given access to the CPU again. So what will happen here is to perform a syscall in /bin/kill, it is send the signal sig kill to the process 35. I return from the kernel mode back into user mode in the current process because that process has not used up its quantum yet. Every process, if it has more work to do, it will be given up to, I think, 100 milliseconds. It's user configurable, and I think we can dig into like systems one or your Docker virtual machine to figure out how much time each quantum is, but let's just pretend it's 100 milliseconds. So if this process has 100 milliseconds of work to do and nobody else has also has work to do, it's going to be given all of that work. So it does all that work, it does all that work, and then eventually the other process, 35, will be switched to. So eventually it's going to say, you've used up your time. It's time for me to go over to the other instruction and figure out, it's time for me as the kernel to determine which process to run next. I'm going to decide, let's run process 35 next. And so I'm going to say, okay, let's go over into the context of process 35. When I get over into the context of process 35, the last thing I do is I set a timer. I say, hey, CPU, if I haven't woken up in the next 100 milliseconds, wake me up. Or 10 milliseconds, or however much it's supposed to based on its scheduling algorithm. And then it gives control back to whatever the next instruction is. In this situation, this is where the signal handling actually happens. Instead of doing a context switch back into user mode in process 35, the kernel says, aha, I have a waiting signal to deliver to this process. I have to send it this sig kill signal. When I see that I have to give it this sig kill signal, instead of running that next instruction, I'm going to run the exception handler for that specific signal. Anyhow, my next slide, previous slide, somehow broke. Sorry. Okay, so signals indicate to a process by setting it some bit that says, oh, hey, this is the signal. And if it receives sig kill, the sig kill bit is 1. And each process has a interrupt vector that that indicates what to do for each of those individual signals. Some signals, the user level process can't control what runs on their behalf when the signal handler gets called. But in lots of cases, in almost all except for 2 cases, they can define what their process is supposed to do when it receives a signal of a specific bit. And so these actions have defaults. There are certain defaults like SIGINT, sigquit, sigil that will by default terminate the process. So if you, as a user level coder, have not yet said, hey, I want to do something special when this signal comes in, it'll just kill your process. Certain things like sigkill and sigstop cannot be changed. You cannot change what your user level code is going to do as a result of a sigkill function or as a result of a sigstop function. Your process will be put to sleep in the sigstop situation. Your process will be terminated in the sigkill version. If you've heard jokes or heard about kill-9 as a way to like kill something no matter what, 9 is the ID of sigkill. And when somebody says, oh, I'm going to kill 9-9 that thing, it's like, I really absolutely positively need to have that process terminate. I cannot allow it to run under any circumstances anymore. So that signal cannot be blocked. It cannot be ignored. It cannot be handled in a custom way. It has to terminate the process. There's some that will terminate the process and then also dump the core. So if you have the memory image of your program and it does a segfault, it's like, well, one really common thing that I would want to do there is take a look at what was going on. I can actually load that core into GDB and it will say, oh, here's what the stack looked like. Here's what the variables looked like. Here's what it tried to do when it caused a segmentation fault. That's really, really useful when you are in the process of debugging a program. And if something makes a bad memory access, it's probably a good reason to, especially if it was running in production, it's a fantastic idea to figure out what the heck went wrong, because that is a bad, bad bug. Yeah, we can also do a stop and continue. That's what sigstop and sigcontinue are for. This is foregrounding and backgrounding jobs. I think I showed this in office hours on Tuesday or last Thursday, something along those lines. There's also default action of just ignoring those signals. Like by default, if a child of mine, this gets so bad. By default, if a child process has terminated, the operating system will send me a signal that says, hey, that child process has terminated. And then by default, nothing will happen because I don't really need to do anything about that. Like, yeah, it will stick around in the process table until I actually call waitpit on it. But there's no like, hey, you need to stop what it is you're doing and handle this child terminating. That's not really a logical thing to do when child process is terminating is a typical expected thing. I don't want to stop what I'm doing. I don't want to pause everything I'm doing and go over here and handle the fact that this process exited normally, right? So by default, ignoring sigchild is relatively logical. Then there's weird esoteric things like the window size changing. There's user-defined signals like SIGUSER1 and SIGUSER2 that don't have anything semantically involved with them that basically say, hey, if process 1 wants to send a signal to process 2 and arbitrarily define what it's supposed to mean, use SIGUSER1 and SIGUSER2. That's what those are there for. Now, when you can, so except for sigstop and sigkill, you can define a new way to handle that signal, and that's what the signal function does. There's a little weirdness here, and I love catching people on these things. The signal function does not send signals. The signal function installs signal handlers. The kill function does not always send the kill signal. The kill function is used to send signals. Hard, annoying, but we will deal with it, right? We can handle this. Now, when we're installing these signal handlers, we can install specially named ones like SIGIGN and SIGDFL. So if I install a signal handler called SIGIGN, that just says ignore this signal. I don't want to do anything as a result of this signal, or I can set the handler back to the default action, which, if it was SIGINT is terminate the program. If it was SIGUSER1, it's do absolutely nothing. SIGCHILD, do absolutely nothing. You can set it back to whatever was supposed to happen after you have defined it to something different. You could, if you wanted to, just have your default action be clicked, right? I could say, oh, when my child process dies, I want to die too. Like, getting ridiculous, but in terms of the analogy, but that is the thing that you could do. And you could say, maybe on second thought, that's not a great idea. You could set it back to SIGDFL, which case there would no longer be something that SIGCHILD would do. let's switch over to our lectures. So here, this is our most basic possible process. And if I GCC this guy, so one, a dot out. So this is a process, and I can send it the SIGINT by hitting Control C on my keyboard. If I were to run this and I just start banging on my keyboard, it just keeps on running, right? This is a normal process. Now, if I were to come over here and I add this signal, so I can say when this process receives the SIGINT signal, I want to ignore it. I can do that. I can just say ignore it. So if I GCC of this guy and I run a dot out, and then I bang on the keyboard, that's expected. But if I hit Control C here, nothing happens. So I am stuck in here. And I need to send a different signal to that process to stop it. I know that Control backslash, if it doesn't pull up my password manager, let's kill the password manager so it doesn't take over Control C or Control backslash. Yeah, so Control backslash sends SIGQUIT, and I did not cause SIGQUIT to be ignored here. We can be even funner. It can be a total jerkwad. And no, not SIGKILL. I want to do SIGQUIT. And I can both ignore int and quit. So if you want to like annoy your friends and have processes run that they can't kill. So I can't kill this with Control C now. I can't kill this with Control backslash now. In fact, I need to go over to another window. A dot out. So I've got a process a dot out here. So this 2614. If I want to stop this process, I can terminate its parent, and it will no longer, it'll error out because it tries to write to standard out, but standard out doesn't exist anymore, and then it doesn't know what to do and it dies. I can come over here and I can send the kill signal to 2614, and that one will definitely kill it, right? So here, there was nothing my process could have done. Let's be fun. Let's do an actual demo of this. So let's do sig kill. This will probably not work, but I didn't try it beforehand. So here, that doesn't work. That doesn't work. Come over here. Check for what its process ID is. Kill-9 of 2605. Come back, and it was killed, right? So even though I told it, hey, I want to do something different when I kill the signal, it doesn't, that doesn't work, right? I cannot mask, block, prevent, ignore the sig kill signal. Now, not only that, but we can do our user level process. So let's see. So we can block, I'll go back over and show a couple more demos in a moment, but just to cover a few more pieces of the ideas here. Sometimes we can block signals in addition to changing what we do with them. Implicitly, the kernel is going to block signals being delivered to your process if it is running that process in kernel mode, because we don't want really important operating system stuff to be disrupted by the fact that some, user level signal ended up showing up. So if I block signals, that's kind of like me, I don't know, where does my my mail carrier analogy show up? Here, this is like some jerkwad coming in front of your mailbox and like holding the door closed. It's like the signal, the flag can go up, and we can say like, oh, we're going to send a signal, and it's going to be pending. It's going to be something we want to deliver, and I'm going to keep that flag up, but I'm just going to hold that door to my mailbox shut. You can't open that mailbox until I have unblocked the signal. So those signals become pending, but they're not received until the signal handler returns. The mail carrier cannot come and open that box until you have taken your hand away and allow them to, pick up your ballot or whatever, if we really want to get topical about this. So while we are handling signals in user mode, we can receive other signals while we're receiving that one signal. I don't even want to try and make an analogy for this, but the basic idea is if we have two different signals that can be delivered to our process, and the world exists such that we could receive the signal, because remember, we only receive our signals when we receive the sorry, I started thinking in my head instead of talking about what I want to talk about. We only receive signals when we transfer over from kernel mode back over to user mode. So if I'm handling a signal and I'm just doing user level stuff and somebody sends me a different signal, I'm going to keep doing that user level stuff until I do a system call or until I get swapped out due to a context switch. When I get swapped back in, rather than going back to where I was in that signal handler, I'm going to go over to the other signal handler. So if I had 50 different signal handlers and I just happened to make it work so that the timing all worked out, that I switched back in before I finished the signal handler, instead of going back to the next instruction I was supposed to run, I'm going to go to some other instruction. This gets really tricky. For different signals, this can happen. But when I am handling a specific signal, like the signal for S, right? So when I'm handling signal S, I cannot receive signal S again. I don't want to create like an infinite loop of signal handlers of the same exact signal. But if I have a different signal show up, I will start handling that. So by default, S gets blocked when you are handling S, but other signals are not blocked while you're handling S. Every other signal could still interrupt your currently running code. Signals aren't just sent to an individual process, they're sent to an entire group of processes, and every process belongs to exactly one process group. This concept comes from the fact that we want to create jobs, and in the Unix model of running lots of different tools that you compose in interesting ways using standard in and standard out, this kind of makes sense to have this concept of a process group where I want to say this whole entire job needs to stop. Or this whole entire job should terminate. So I can send a signal to the entire process group. And these process groups are used when you're indicating that a bunch of processes work together. Children belong to the same group as their parents, and they can change their group ID explicitly by calling a system call. So if I wanted to run a program called yes, and and that just sends the character Y as much as it possibly can to whatever process is connected to its standard out. I can link those processes together, and then I want to remove every single file, and I want to say yes to whatever prompt RM gives me. I can pipe that process yes to that RM star. These are linked together in a single job, and there's lots of very, very powerful things we can do using things like sed and awk and grep and sort and all of these, and xargs, all of these different tiny little programs can be composed to do very, very complicated things very, very quickly at the shell. It's a little bit out of context or out of scope for this class, but that is this Unix philosophy is a very important, powerful mechanism if you're doing a lot of data-driven system administration, developer work at the terminal. Very, very powerful mechanism. But that gets represented in Linux by this concept of a job where you have lots of different processes that are connected in some way. Like yes and RM here are two different processes. They're connected by standard in and standard out, but more importantly, they are a thing that a user wanted to do. They're a task, they're a job that is one big unit. Now we have foreground jobs and background jobs. There's some situations where we want to just cause something to run and we don't want it to take up our terminal. We just want it to continue running in the background and we'll keep doing our work. We put our ampersand there in front of or at the end of a command line, which says rather that the shell should fork itself, it should exec this other program, but then instead of waiting for it to end and then giving control back, it should just immediately give control back to the shell so the shell can keep doing what it wants to do. So if I wanted to do like a VS Code and I was on a Linux machine, I would fork it off like this. I want to launch it from my terminal and it's going to be some window by itself, but I want to keep running GCC or VI or whatever the heck it is else I want to do at that terminal. I don't want that terminal to just be frozen until this program terminates. So every terminal, like every one of these virtual terminals, has one foreground job and any number of background jobs. So that foreground job is the thing which is intended to be writing to standard out and reading from standard in at that moment in time. We already talked about sending signals with the kill function. Where do I want to get to? There's a few other important pieces of information in here. Yeah, so writing signal handlers is tricky. This is hard part. This is probably the next important section of this video. So we're going to explore concurrency, like actual concurrency issues a little bit later on in the term. But for now, we're going to just go over some relatively basic guidelines for what to do here. So I'm going to switch back over to my demo stuff. So in addition to installing signal handlers like we have here, we can also, in addition to installing like a ignore signal handler like we have here, we can also install a signal handler that does something in and of itself. So here, I'm going to install this function. So I'm passing a reference to this function. Remember, this is just a symbol, and that symbol refers to a location in memory. That location in memory just so happens to have an assembly instruction that is the beginning of a function. So if I were to GCC this one right here, signals 3, and I want to run a.out. Here again, I'm counting like 4 times a second of what, just for fun, I guess. And if I hit Control C here, I will send I'm going to write to standard out this message, you can't stop me. So if you want to be a total jerkwad, you can do that. And of course, again, we can Control / right here. What's really important is that there are there's 3 places where this signal could potentially be delivered to this process. It's going to be after a system call, like printf. Printf will eventually call write. And if the signal was sent, if I hit Control C during the few microseconds that it took to run the write system call, then as my code transitions back to user mode at the end of the printf statement, at the end of that write system call, instead of running the next instruction of my code right here in main, however that got compiled, I am instead going to run the first instruction of signal handler, which is a little bit tricky because while I am going to get my own stack frame in signal handler so that it can have its own local variables, I don't have my own global variables. I don't have my own anything really to do stuff on like independently of the main thread. And this like immediately to me, it's like, oh, that's not that big a deal, right? Like just do whatever you need to do. But there's a lot of functionality that relies on global variables. There's a lot of things which you cannot do here. I had to write this write system call basically manually here so that I didn't do something that is not safe to be called from a signal handler. If you take a look in the book, there are many, many library functions. The standard library has a small handful, and there's hundreds and hundreds of functions in the standard library. These are the only ones that are safe to be called from a signal handler. You can see write is in there, but printf, snprintf, fgets, fputs, puts, getchar, getchar, all of that stuff is not in there. There's a lot of things that are unsafe because they're going to be interacting with the outside world of your user level process outside of just your own individual stack frame. And so that's one of the big hard parts about signal handling is because I interrupted this code instead of running line 21, right? Because like when I think about programming, in a normal world where this didn't exist, where I didn't use a signal handler, if I ran this line printf, I know as the programmer that one of 2 things is going to happen next. Either the assembly instruction that increments counter will happen next, or my program is going to die, right? Those are the only 2 things in the normal non-signal handler world that could potentially happen next. And if I modified counter in that signal handler, then counter might get bumped up by 2 instead of by 1, or it might get set back to 0 or something. And if I'm reasoning about my program and what it's supposed to do, like if I wanted to, if I was reasoning about my program and what it would do, in a normal world, I can be safe. Like I can know without a shadow of a doubt that if I run this code, this is going to print a number. And then that same number is the number that's going to get incremented here. If I had access to counter up here in this signal handler, I could change it to minus a mil, or like a million or 0 or some value arbitrarily. And this code would no longer have the invariance that it expected. That's the super hard part about concurrent programming, when you have different threads that are threads of control that are going to run at different points in time, and you can't be sure of when which one runs and when which other one runs. Now, when we get over to the final module of class, we're going to learn how to actually really solve that problem. But for now, we're kind of going to say the best thing to do to prevent that from being a problem is that when we run our signal handlers, we're only going to do things that don't have unexpected impacts on the outside world. If we only work within our own little stack frame of, say, our signal handler, then when it gets thrown away because the signal handler returns, it's not that big a deal. We know that things are going to work the way that we want them to, and we're not going to have to think about these really, really gnarly problems of concurrency. So this is all to say that, yeah, we're going to have our guidelines. We write our signal handlers, and let's go over our guidelines. So these are the same guidelines we have in the book. These 6 things telling you to keep your signal handler simple, call these async signal safe functions, save and restore error. Remember, error is a global variable that the C standard library uses to keep track of what the error state of a specific function is if its return value can't give you a real error code. Like if the return value has to give you how many bytes were read, and you can't send a specific error, because if there's 17 different errors, like what do? You want to say, I sent 7 characters means the special thing. You can't do that. So instead, what the C standard library does is it uses a global variable error, which you can then interpret using those p-error, str error functions. You can, if you're doing something that is going to deal with very important data structures, you can temporarily block signals. This can say, listen, all these other signals need to stop. I'm going to do something that's very important that is going to manipulate the status of this process. If you do an strace on your shell, when it launches a new program, you'll see a lot of sigproc mask, and that is masking off signals, basically preventing them from being delivered until it finishes a very important chunk of code. When we declare global variables as volatile, this prevents the compiler from storing them in a register. This means that if we're ever going to manipulate the value in this variable, it must be immediately persisted to memory. It cannot be stored in a register until it gets persisted back to whatever address it lives in. Typically, you don't have to do that. The compiler can optimize to, rather than keep something on a stack frame, it's just going to keep it in a register, which makes things much, much faster. Remember that registers are just amazingly faster than even your L1 cache. So it's a really good idea to not just use volatile left, right, and center. You don't want to use that everywhere. But if something has to always have the correct value stored in memory no matter what, you can set it as volatile. And there's also the sigatomic T that basically means that not only is reading that value out of memory always going to give you the right value, but writing to it is also always going to give you the right value. It's an atomic write, which means that whatever you do to write to that variable happens in one instruction, no matter what. So flags that are installed this way don't need to be protected with any synchronization primitive. They don't have to be protected with blocking signals. They can just be manipulated like I'm going to show you in my demo code pretty soon. So let's go back over to our demo code. So if we go over here to, this is a decent, safe way to receive a signal and then do something based on that signal. So first, we have a volatile sigatomic T. So this means volatile here means that keep running will never be stored in a register. It will always have its correct value in memory. The sigatomic T means I can write to it, and it won't cause some inconsistent scenario. And we make it static because we don't want anybody else outside of us to have their own keep running, manipulated by our own keep running, right? We know that this is only for us to see. Now, when we run our signal handler, we need to do async signal safe things. And that means async signal safe system calls, like write, or I guess this is a library call technically. We can do if statements based on these things. I can set a value to keep running. That's also safe to do. And the most important high-level bit here is that I'm not going to do things like exit this process in the signal handler. I'm not going to clean up. I'm not going to fix whatever went wrong. I am purely going to say, if this signal got delivered and it's something I need to eventually take care of, I'm going to set a flag in my code as opposed to in the kernel's process table that says, hey, you need to do something when you get around to doing it in the main execution thread. That's fundamentally what we're doing here and what we'll be doing in some other assignments later on in class. So here we install our handler for SIGINT, and we check this flag to see whether we're supposed to keep running or not. And we do everything that we were doing before. And we peer if our sleep fails. And if I GCC this sucker right here, signals 4, and I run it, I can control C here, and I can do things in the signal handler, and I can tell it to stop running, and then I actually check it in the main thread. So every single time I go through this while loop, I am checking whether keep running is true or not. And I only keep running if keep running is there. You could imagine that you could use, rather than this, you could have something like while true, and then you could have, if special flag bang equals 0, then, do what you need to based on the fact that the signal got delivered, right? So what we can do is we can say, aha, thank you, operating system, for interrupting us in the middle of our program and delivering this signal. I'm going to deliver that to the main thread when the main thread is ready to handle it. Until then, my signal handler will be done. And that's a safe way to do things like this. But it would not be safe to do, it'll almost always not be safe to do whatever special things you need to do in your signal handler. That is how we get around the challenges of concurrency with respect to signal handling. I think that's about what I wanted to have there. Okay, now, how signals actually get delivered. This is probably the next main section of the video right here. The kernel is going to maintain these pending bit vectors and blocked bit vectors for every single process. Each bit corresponds to an individual signal, and they're bits. They can be set to 0, which means there's no signal pending. They can be set to 1, which means there's a signal pending. What's really important here is that you can't set one bit to 2 or 3 or 4. So I can't say I delivered this signal 7 times. There's no way for the operating system to keep track of the fact that that signal got delivered more than once. It can, or got sent more than once. It's really hard to keep all of these all this terminology separate. So you send a signal that raises the pending bit. When you deliver the signal, that's when the bit gets set from 1 to 0 and it actually gets handled by the user level process. So you can only have pending set to 1. You can't have pending set to 2 or 3 or 4. For a specific signal, you can only have it pending once. No matter how many times someone has tried to send you sig user 1, you can only set that bit to 1. You can't send it to 1 really hard, right? So I can send 17,000 different sig user 1s, and only one of them could potentially be delivered. That's the trick that we're worrying about right here. Spoiler alert. Likewise, blocked is also a bit vector, but that's a lot more semantically consistent, if you want to be fancy about it, right? That means that this process has said, I do not want to receive this signal right now. So if that signal is pending, the kernel is going to say, don't care, I can't deliver it until it has been unblocked. Once the user level process has decided, I am willing to receive the signal now, then boom, the kernel can just be like, gotcha, you got a signal that you have to take care of. And then it'll take care of it. But until then, it doesn't worry about it. The things, the system calls that deal with signals, most common ones here are wait, sleep, and pause. So wait allows us to block our process until we receive the sigchild signal. So this puts us to sleep until a specific signal is ready to be delivered, and then it just gets delivered. So you can use wait like we did in last week's lecture without installing a signal handler, right? We get blocked until we return, and sigchild gets ignored. But in this case, it gets ignored, and then your program continues running, which is super useful. Sleep, not use sleep that we just used, but the sleep system call will block our process until one of two situations. Either A, the number of seconds that you asked to sleep has finished, or B, any old signal at all got received. It will immediately move on to the next line of your code. So I can show something a little bit maybe unexpected. So I come over here to my most basic example. Let's do this, and then let's do sleep for 3 seconds. And then let's do int result equals 0. Result equals this. Printf. I still had 2 seconds to sleep. And then result. Nope. Result. Printf is spelled incorrectly. And then UCC signals 2. So if I send, so that makes sense. I still had 0 signals. Oh, wait, oh, this is the one I've got to kill from another window. Fantastic, Chris. Kill 4339. And sig kill doesn't send kill. Oh, it does. Sig term. That sends sig term, which can also be masked. Right? By default, kill sends sig term, which is different from sig quit, which is different from sig kill, which is different from sigint. There's lots of different ways to stop a signal. So let's nuke all of those, make it again, run it here. And sigint is not ignored, and therefore sigint terminates the process. So I do want to only have that one, GCC this sucker. What the heck? Come on. Why is this not doing? We're in the middle of the sleep. I guess when I ignore it, it doesn't even stop the sleep. Interesting. Let's say, I had an example where this was actually working. Let's pull this in here and set this to sig handler. See if this does what I want it to. Yeah, okay, so that works. So if I handle that signal and then I return control back, what's really, so this is actually a really interesting example I have right here. First, I suck at typing when I'm really, really trying to go fast. Second, I am trying to count. And third, I have sleep returning here. So what can happen to system calls is that sometimes signals can cause them to return prematurely. So sleep here gets returned prematurely and it doesn't retry that system call. We can sometimes ask to retry a system call if it is retryable. There's some stuff at the very end of 8.5 that talks about this. But the basic idea here is that I was running the sleep system call and I said, please sleep for 3 seconds. That sleep for 3 seconds did not complete because I lost my face cam. All right, hopefully this didn't overheat, kill itself. Yeah, anyway, what's going on next? Oh, we're okay, we're okay. So where was I? You go into the kernel because you called sleep. Sometimes you're not just going to be guaranteed to sleep for 3 seconds. Sleep, as we saw on this slide, implicitly is saying either sleep for that many seconds or continue after you receive a signal and handle it. So that's the important part here. There are some system calls that are going to be interrupted and they aren't going to finish what it is they were supposed to finish. They're going to instead go back and do something else. Usually they will tell us, hey, this got interrupted. There is a specific error no, like EINTR, what is it? Like it's EINT. I don't think I have error no in. That I show this. Yeah, so EINTR is the error that means that your system call got interrupted. That is probably what would happen as a result of that. So if I do a P error here, just return from sleep. Yeah, so there's success in that case, right? Error no is not set to anything, but if I control C this, I get EINTR, which P error will helpfully tell us means the system call got interrupted. So sometimes if you receive a signal, it can stop a system call that you're doing. You were reading from a file and it didn't finish all of what it needed to do. It got interrupted. You'll get an error that says that that happened. And then sometimes it can be retried. You can ask the system to retry it, but sometimes it's just not going to work. So when you are sending and receiving signals and trying to handle them instead of just letting your program die, which is what typically signals do, like you control C and it kills your program. Okay, big deal. I guess I didn't need that program anyway. That's not that big a deal. But when you're actually trying to recover from the fact that you received a signal, this is another thing that you need to be aware of. Let's kill this for now. Okay, so pause blocks us until we receive any signal. So that's kind of like sleep infinity. Wait, puts us to sleep until we get our child signal. And that's about all I had on the slides. Let's switch over to tricky 1 and tricky 2 for now. So these are examples that are in the discussion questions. And I'm not going to go over them in the videos. I'm just going to straight up give you the answer. But if you do want to experiment with these from the discussion questions, you're more than welcome to actually take a look at it. We'll talk about these during discussion, during during, what's it called? Kahoot time. And if you want to experiment with them right now, they are in this VS Code Lectures repository. Thanks so much for watching. Again, let me know whether this off-the-cuff version instead of the fully edited version seemed just as good. I ramble a little bit more, but when I'm on camera live, I can usually keep the rambling to a minimum. So thanks so much, and I'll see you next time.